Hello everyone, my name is Being Beast and today I am going to present you a tutorial on powder XRD for characterization of nanoscale materials. So the content is going to be PXRD instrumentation, its theory, pattern, difference between bulk and small crystalline sample, preferred orientation in nanoparticles, preferred orientation and intensities, and finally the conclusion. PXRD. PXRD full form is powder X-ray diffraction. It is a characterization technique which can be used for nanoscale materials. With the PXRD, we can actually find out the phase identification, composition, crystallite size, and morphology. Since it is a bulk technique, so the information that we get from here, you can compare it with some microscopy data to test whether a small number of particles are actually the correct representation of most of the samples. PXRD. So this is how PXRD instrument look like. Now let's dive into it to find out how are the different components look like. So the first component that we need to focus is X-ray tube. The X-ray tube that we are using the source here is copper. So copper can release many types of radiation like copper K alpha, copper K beta. Depending upon what we required, we can use a incident beam optics, which can only and only give the requisite beam according to our input. The third part is the sample holder. The sample holder is actually a groove in which we place our sample. Then there is a goniometer circle that tells you how much angle you are going to measure, by the which also the diffraction angle. The fifth one is the X-ray detector. So this detects the incoming radiation from the atomic planes. Powder XRD theory. So powder XRD theory is based upon our Bragg's law. So diffraction occurs when light is scattered by a periodic array of long range atoms which produce constructive interference at specific angles. In atoms, actually, the electrons which are playing this role, they do, or they try to undergo, when the beam is passed upon them, they will undergo constructive interference, and the amount of light scatter is proportional to the amount of electron the atom hold. So as you can see, the rays are coming to the atoms, or the much, I can say that electrons, and it is getting reflected back. See here. Okay. Yeah. So now PXRD. So there here we have taken example of Woodside CDS. You can see 100 plane are there, 002 plane are there, 101 plane is there. Okay. So yeah. So these are the planes. These are the most intense planes that we have taken. So that means the CDS, if we are going to do PXRD of the CDS nanoparticles, so these are the most intense peaks that we will see. Okay. After that, we will move ahead, and you can imagine that x, z, and y. X in the x-axis, like x is like the on the horizontal, z is the vertical, and y is coming out of the plane. So for this three planes, we have shown the atoms like this. Okay. So yeah, CDS nanoparticles will have its band gap, color, electronic, optic properties is dependent upon the size and shape. Okay, so you can imagine 50 nanometer will have different properties. Nanoparticles will have different properties as compared to 5 nanometer. Most stable structure of CDS, it's Woodside. Okay, let's move ahead now. So here is the Sacheri equation. So Sacheri equation tells us that crystalline domain size is actually equal to Sacheri constant K. Lambda is there, which is the wavelength. Beta is the peak width at half of height, and theta is the diffraction angle. Okay. So now you might be wondering that, okay, this is saturated equation. Now this is the thing. So what I'm trying to say, if you compare bulk and small crystallites, you can see that, okay, there is a sharp peak over here which decreases, right? The red one you can see, right? Okay, let me just focus. Yeah, now you can see that the domain size is inversely proportional to peak broadening. Domain size d inversely proportional to peak broadening. Okay, so you can see that from 1 micrometer to 25 micrometer, the peak sharpness decreases and it broadens. Why does it happens? So as the size of the nanoparticle decreases, the more it will get randomly oriented. Okay, since it get more randomly oriented, so you will not get a very good constructive interference at lower intensity. That's why you got a broader peak. Okay, now you can see that further decreasing the size from 15 nanometer to 10 nanometer, the broadening is significant and the signal intensity to noise ratio is very low. Okay, and it is very difficult to distinguish the peaks now. And 5 to 1, you can see that they are flat, right? So it is very difficult, even further difficult than 15 nanometer to do here. Okay, Yeah. So what should we do? If we apply TEM analysis and it shows that average diameter is of 10 nanometer, but XRD pattern has sharp peaks, that means that the majority of the bulk sample is not composed of 10 nanometer. It is only represent a minority subpopulation. Okay, good. Moving ahead, preferred orientation. So preferred orientation, just like nanoparticles, they can be of different types. Like you can imagine that to be on circles or in cubes or in cylinders. So the main thing or the focus that we have to give upon is like the game we used to play in our childhood, like Tetris. Bricks will come and then we try to orient it. Similarly, in that way, the randomization is very more in the spherical one, but the sphere, the cube one, as you can see over here, they will have a certain face, right? So cube will stack upon the certain face, just like in the Tetris game, in which we try to place the bricks, right? Okay. Okay. Now you can see the peak position remains the same, but relative intensity changes upon changing the concentration. So from bulk you are getting to like 99% of the nanoparticles, right? So you will see different orientations. Okay. Now we have taken another example of germanium sulfide. What is happening over here? So you can see the picture A shows that it is like the preferred one is 200. The B is like the, as you can see, it is a high resolution one. Okay, transmission or not high resolution, just a normal TEM is there, but it's a bright field, right? The background is bright, so it has a bright field TEM resolution. The C, okay, yeah, let's talk about the C. The C actually tell us that we have done what we have done in the C. We have simulated the germanium sulfide, and then we try to experimentally do it just to see that how close we are to the, how close the theoretical one is equal to the experimental one. So we can actually see that the peaks that are thought to be, okay, either you can do one thing, you can do either you can allow certain preferred orientation to do, or you can minimize those. So what we are doing in GS dropcast experiment, we allow to grow a certain orientation, 400 plane, 100 plane. Okay, so 100 is preferred, so similarly 400 is preferred. So you can see that the peak is dominate in the GS 100 preferred orientation simulation in the red one, and that similarly we obtained on the green one. Okay, so from this data we know that yes, preferred orientation has effect on the intensity. Okay, yeah. So yeah, you can either prepare your XRD sample, either you minimize or maximum preferred orientation to evaluate if variable intensity varies with the orientation effect, and which we found yes, it varies. Now another example of CD is there. So you can see there is a 5 nanometer sample, there is a 25 nanometer sample. If you combine these two things, what will happen? 5 nanometer particles show broad peak, 25 nanometer particles show sharp peak. If you mix them up, you will get the blue one. So blue one contains sharp peak and broad tails. Okay. Okay, moving ahead now. So these three, now what we are going to do, these are the cobalt sulfide nanoparticles. So you can see on the left hand side 100, 002 and 101 are the most intense one. Okay, there is a HRTM for this COS nano platelet. Okay, and third is the representation of the thickness in the direction of the nanoparticles. Okay, so how to measure the direction? It is very easy. From the plane, just draw a perpendicular, so you can actually get the direction. Okay, so the direction of x are like 30 nanometers straight, 8 nanometers like a little bit diagonal, and 5 nanometers like horizontal. Okay, with different spacing. Okay, now in the cobalt sulfide nanoparticle example, what we are trying to do, the woodside CDS has some peaks, and the zinc blend CDS will have some other peaks, and those peaks are like totally like different. Okay, but you can see if you try to combine zinc blend with woodside, the blue one will have some peaks as like resembles of zinc blend, and some peaks that resemble woodside. Okay, and if there are some peaks that are on the same side, then those peaks will increase. So you can see that peaks around like after 40 degree, you can see that there are some peaks which actually enhance in the blue one. Okay, and similarly the second peak around 25 degree, can imagine, is also increase in height. That's because they are in the same plane. Okay, right. So yeah, now if you imagine woodside CDS to be of 001 preferred orientation, the peaks actually matches that of the 1-1 mixture. Okay, good. So careful, therefore careful analysis is required to differentiate between the scenarios that can lead to similar XRD, right? So the composition are totally different, but you are actually getting the similar XRD. So you need to be very, very sure that, okay, whether the composition is 35% or 50-50%, then you can use some another techniques along with PXRD. Okay. So what is the conclusion? Conclusion is you can get the nature of the sample depending upon, you can get like nature of the sample, like we can use it on sinter sample, metal foils, coating films. Even it is like you can actually find out the texture of some materials from using PXRD. Phase identification, composition. So diffraction pattern of every phase is unique, just like our fingerprints. So it uses the position and relative intensity of peak, and that tries to match with our experimental data to get the reference that pattern in the database. So if it matches to that in the database, we can say, oh, these planes are will be present in my newly created material. Sample purity. For sample purity is that actually required, or like you cannot find like 100% sample purity from this. You can know that these compounds are present, but to be sure that sample purity 100%, it is not possible. Why? Because we remember, right, there are some small peaks having low value of signal to noise ratio. You cannot detect that. That is can be existed as impurity. So you require some assistance of some another techniques, just like we have seen TEM or something else. Okay. To find the sample purity. Done. Lattice constant. So lattice constant means the alpha, beta, gamma, or ABC. Those are your lattice constant. So highly crystalline sample with signal to high signal to ratio and high sharp peaks. Lattice constant can be reported with 3 to 4 decimal plate, and they can be resolved using LAB6. Okay. Now average crystalline size of nanocrystalline samples. So we have already discussed this part. It is difficult to distinguish between amorphous and nanocrystalline sample because they all show broader peaks. Okay, if the nanocrystalline size is very, very small, so it also shows broader peak. So what is the Weygot's law? That is the last thing that we need to discuss today. So gold and Ag, if when you talk them in a alloy, they show surface resonance plasmon energy, and change in composition changes property of nanoparticles, and actually they both will be present in similar, okay, very, very close, or you cannot detect them very actually because the planes that they lie are very close to each other, very, very similar. Okay, so it is difficult to, and there exists a linear relationship between lattice constant of alloy and its composition. Thank you everyone, that's all for today. Thank you, bye bye.